All right. Okay. So then it's my pleasure to introduce our speaker today, Andrew Wagenmaker. He's a fourth-year PhD student in computer science at the University of Washington, supervised by Kevin Jamieson, where he's supported by an NSF graduate research fellowship. Before that, he did a master's and bachelor's degree in electrical engineering at the University of Michigan. And currently, he's interested in studying active learning, reinforcement learning, and control theory, and bandits. He has already published a bunch of really good papers. And today, he's going to be telling us about instance optimality in PAC reinforcement learning. So with that, the floor is yours. Welcome, Andrew.
Yeah, thank you for the introduction and also for the invitation to present here. I'm really excited to be talking about this work. So this is a joint work with my advisor, Kevin, as well as Max Simchowitz. So as we sort of all know, reinforcement learning has had many different practical successes over the last few years, whether AlphaGo, various robotic examples, other video game examples. And a commonality between a lot of these works is that to come up with a good policy to solve one of these tasks, you often need a very large number of samples, a large number of interactions with the environment. And so for certain tasks, for certain problems, this is feasible, but for oftentimes we simply may not be able to collect this many samples or not be able to collect this many samples easily to solve a particular task, which limits the situations where we can really apply RL. And so to some degree, certain RL tests are simply hard. Theoretically, we have lower bounds. We know that some tasks simply need a large number of samples to solve, and we can't necessarily do better. But we might be able to approach this from another angle and say, well, perhaps we can't solve, perhaps some tasks are just hard and need a lot of samples, but perhaps on easier tasks, we can do a lot better. And so for instance, we can think about two tasks where on one hand, we have a simple robot traversing a maze. And on the other hand, we have an autonomous vehicle. And obviously, finding a good policy to traverse this maze is going to be a much simpler task than finding a good policy to drive an autonomous vehicle. And so ideally, we would want an algorithm to be able to perform well, to take advantage of the simpler structure on this easy example, while still performing reasonably well on this hard example. We want algorithms that scale with the actual problem difficulty, not in some worst case sense. And so we want algorithms that are sort of adapting to the underlying structure in the problem. And so if we can come up with algorithms like that, perhaps we can chisel into this sample complexity barrier. So this is sort of the first question we're trying to answer in this paper, which is, can we come up with instance-dependent sample complexities for reinforcement learning? And the second related question is, are existing approaches handling this properly? Are existing approaches that we're applying, are they addressing these sort of instance-dependent quantities? Are they taking advantage of the instance-dependent structures in the problem? And so as I've been saying, we're really approaching this from an instance-dependent perspective. We're concerned here with deriving bounds that scale with very granular properties of the problem, not in the worst case sense. And I'll get sort of into the more definitions of what I mean by that. Okay, so this is sort of the motivation. The sort of, to make clear what the problem we're actually studying is, we're going to be looking into finding good policies. So this is typically called the PAC RL setting. We're not interested in low regret, the more online version of the problem. And so we have an agent that's interacting with the environment. We don't care sort of the reward the agent collects while these interactions are occurring. All we care about is that it returns a good policy at the end. And we are working in the online non-generative setting, to be clear. So where are we at sort of with this PAC RL problem? Well, this has been studied for quite some time, since the early 2000s. And the majority of papers out there have sort of a result that looks something like this. After S, the number of states, times A, the number of actions, times some polynomial in H, the horizon, times epsilon to the -2. After you collect this many episodes, then you can output an epsilon optimal policy with high probability. Right, and this is sort of minimax optimal. We have sort of results that are optimal now, even in terms of H. But it's also still very coarse, right? It doesn't disambiguate between two MDPs that might have the same number of states and actions, where one MDP might be much easier to solve than another MDP. But this is sort of the majority of the results out there in PAC RL look something like this. And we can also do something which is commonly referenced in the literature, which is called the online to batch conversion. So we can run a low regret algorithm. And if we just take one of the policies played by the low regret algorithm, you can show that this would also hit this minimax PAC rate. So even running a low regret algorithm, in a worst case sense, solves PAC RL. But this is, again, sort of this very like coarse worst case perspective. And so what about instance dependent? Well, there isn't actually that much work out there yet on instance dependent RL. My collaborators on this paper had a paper from 2019 where they showed that you can get instance-dependent regret scaling as log k divided by the gaps. And I'll define the gaps in a bit for those not familiar. And you can use this then with this sort of online to batch conversion I mentioned in the previous slide to get a PAC guarantee that scales as 1 over epsilon times the gaps. And then you get a kind of different delta scaling because of the way the online to batch conversion works. But the point is you can still get this sort of quantity that is instance dependent in the sense that now we can get PAC learning that scales with the gaps. But I would argue that this doesn't actually capture all the structure that we might want to capture for PAC learning. For instance, this doesn't capture anything to do with how difficult certain states are to reach. So some states in an MDP might be incredibly difficult to reach. And we don't really want that complexity factoring into our PAC RL bound because, well, if a state is hard to reach, learning a good action in it isn't actually important to learning a good policy. And this bound isn't actually capturing that sort of structure. So it's sort of a first step, but it's not really getting to where we might hope to get. So another work, this is now in the generative setting, so where you can just query arbitrary points. This is by Zanet et al. In 2019. And it's in some ways maybe the most comparable to what we're doing. But they come up with a PAC bound that scales as 1 over max of epsilon squared times delta squared. And there's 2 shortcomings with this. One is first it's in the generative setting, so it doesn't answer this question of exploration, which is one of the key issues in RL. And the second is that it always scales at least as s over epsilon squared, because you always have an action in every state that is optimal, so you always have a 0 gap in every state. And then the final work I'll mention is a very recent work. This came out, I think it was posted to arXiv in June or so, by Majarni et al. And they study best policy identification. So the case where you want to not find an epsilon good policy, but simply find the best policy. And they obtain the following complexity. And I won't go into too much detail with the notation. I'll describe it later. But basically, the idea is you have this W, which quantifies the visitation, and you have this gap. And so this is really what we might hope to get, right? This is sort of capturing this visitation distribution dependence, as well as this gap dependence. Now, the issue with this result is A, is purely asymptotic. And B, it only holds for best policy identification. In practice for RL, we want to usually not do best policy. We want to just find a good policy. And we want to do something in finite time. But this is sort of where we're at. This is the state of PAC RL. And so in this work, what we're going to be looking at is, can we build on this work to come up with a better idea of instance-dependent PAC RL? And sort of we make several contributions. The first is we propose this new notion of complexity, which we call the gap visitation complexity. And I'll go into more detail on this a bit. But the basic thing to notice right now is that we have this complexity term, which scales as the gaps here, epsilon, as well as these visitation probabilities, WH pi. And so it sort of captures this much more granular notion of complexity. And then we propose an algorithm, Mocha, which we show can identify an epsilon optimal policy and roughly sample scaling as the gap visitation complexity for that MDP. And then the final thing, we show that to sort of answer the second question we posed, which is sort of what are existing algorithms doing? Are they taking into account the instance-dependent structure? We show, in fact, that most existing algorithms are not. So we can show using this instance-dependent quantification that pretty much all low regret algorithms can be arbitrarily suboptimal if your goal is to find a good policy for PAC RL. OK, so that's sort of the like high level what we're going to be talking about. Any questions on the motivation problem setup before I dive into some of the more details on it?
So I think you're probably going to formally define the PAC RL setting because what you've been explaining so far doesn't exactly line up with my idea of PAC RL because often historically PAC RL gives a bound on the number of times, the number of episodes in which you play an epsilon suboptimal policy or like a worse than epsilon optimal policy. So that is not really related to outputting.
Right, yeah. So I will define it in the next few slides. I think the sort of distinguishing factor is oftentimes in the That's typically more in like the infinite horizon case where you sort of just like playing continuously and you care about the number of mistakes. Whereas in we're looking at the finite horizon episodic case, and so there you sort of are concerned less with like the number of mistakes and more just can you output a good policy in the end.
Right. So I mean, I'm not really sure like what result was corresponding to which setting, because I had the impression that some of those upper bounds, like that you mentioned, were considering this number of mistakes. But yeah, anyhow, I guess you could have defined this formally. And,
yeah, I think there is pieces in the literature, as you're saying, which is doing just that, which is looking more at the number of mistakes. But that is also very actually related to regret, whereas we are much more interested in this like pure exploration problem, where like the goal is not sort of what you're doing when you're online, but it's what you can return at the end. So I'll define it formally. I think, yeah, you could point to different works in the literature that sort of look at both of these problems. But
all right,
this is what we're looking at. Yeah.
All right, thank you.
Okay, so just the basic notation, we're going to be looking at tabular RL in the online setting. And so basically you have a set of states, a set of actions, a horizon, a transition, a P of H, and we assume this is non-stationary, so the transition can vary from time step to time step. We also assume there's some initial state distribution P naught, and then R of H is a random reward, which we assume is in 0 to 1. So the interaction protocol is basically as follows. You have an agent. He plays an action at time H. And then the environment returns a reward randomly from the sort of reward distribution at this time step with this action. And it returns the next state, SH plus 1, which is sampled from P of H, given that you're in state SH and play action AH. So you do this for H steps, and then the process resets. And we'll assume that all of the initial state distribution, the transitions, and the rewards are all unknown. And just for another notational thing, we're going to let pi in general refer to policies. It's just a mapping from states to actions. So this is sort of the basic setup, pretty standard online episodic RL. And we're going to define a Q-value function, again, in the standard way. So Q of H pi of SA is simply the expected reward you'll obtain if you are in state S and play action A at time step H and then play policy pi for all subsequent states. It's the standard definition. V of H pi is the value function at state S, given that you play policy pi. And we'll use Q star and V star to denote the optimal value functions and pi star to denote the optimal policy. We'll also define here the value of a policy. We'll call it V naught pi. This is simply the sum over the initial state distribution, basically the expected value of the policy over the initial state distribution. So all of this is like the standard RL definitions. There's nothing new here. And so it'll be important in this paper in particular to look at the gap, the suboptimality gap. And so the suboptimality gap, this has appeared in the literature before. And it's defined as follows. We're going to use delta H of SA to denote the gap. And it's basically the difference in the value you would, the optimal value you could obtain in state S at time step H versus the expected value you will obtain if you play action A in state S at time step H and then play the optimal policy. So sort of how suboptimal you would be by playing action A if otherwise you play the optimal policy. And then we're going to introduce this notion of the effective gap here. And so we're going to define the effective gap. We're going to use a delta tilde. And we're going to define it to be simply the gap if the gap is greater than 0. And if the gap is equal to 0, if A is an optimal action, and it's a unique optimal action in this state, then we're going to define the effective gap to be the minimum gap in that state. And so in this case, if A is a unique optimal action, the effective gap will always be greater than 0. Now, in the case where A is not a unique optimal action, we're going to define the effective gap to be equal to 0. So when you see this delta tilde, you can really just think of the gap. It just is sort of for technical reasons, it's helpful to define it in terms of this minimum gap too. And then the final thing I'm gonna introduce is this notion of a state action visitation distribution. And so we'll denote by WH pi SA the probability that at time step H you are in state S and play action A under policy pi. And similarly, WH pi of S is the same thing, but just defined without the A. And we're also going to introduce this notion of maximum reachability, which we use an uppercase W to denote. And this is simply the how the expectant, basically how easily you can reach state S if we play the policy that is most likely to reach it. So it's just a soup overall policy is a WH pi. And then sort of we're going to define the PAC RL problem in the following way. So the goal here is to identify a policy pi hat in as few samples as possible that is epsilon optimal with probability at least 1 minus delta, where we define epsilon optimal to be the value of the optimal policy minus the value of pi hat is less than epsilon. And this is, again, essentially a pure exploration problem. We're not concerned with the reward we acquire in this exploration phase. All we're concerned about is sort of if we can come up with a good policy at the end. So that's the setup. Any questions there? Okay. Okay, so now we can get into the results. So first I'm going to introduce this, again, I sort of mentioned this notion of the gap visitation complexity earlier, so I'm going to introduce it a bit more formally here. So now that we have this notation, we see the gap visitation complexity for a given MDP-M. It sort of balances this trade-off between the state visitation distributions and the gaps. And I'll give an example in a second, sort of that explains like how you actually get this. But the important thing to note is that it sort of depends on how easy it is to reach a state, as well as how difficult it is to sort of identify an optimal action in a state. And it's just sort of dependent on the best possible policy in a sense, right, over the worst possible state in action. And we're also going to introduce this idea of the best policy gap visitation complexity, which essentially you can think of as the best visitation complexity if you let epsilon go to 0. And so this is basically simply the, again, the inf over pi, the max over all states and actions that have gap greater than 0, and simply 1 over the visitation times the gap squared. Okay, so how do you get, or what is the intuition for this? Well, so we can think about multi-arm bandits a bit here, because that sort of provides sort of the intuition for how you get this. So for a multi-arm bandit, the standard complexity of finding an epsilon good arm is the following. It's simply the sum over all actions over all arms, the minimum over 1 over gap squared, and 1 over epsilon squared. So if an arm is really bad, if the gap is really large, then you quickly identify that it's bad, and you only have to pay 1 over gap squared samples for that arm. But if the arm is really good, if it's close to the optimal arm, or epsilon close to the optimal arm, then you don't pay 1 over gap squared, you only pay 1 over epsilon squared, because you only care about identifying this epsilon optimal action. And so the gap visitation complexity really generalizes this idea to MDPs where now navigation is required. So what I have here, this is, you can show, this is slightly different than the form I put on the previous slide, but you can show their equivalent. And so basically what you see is that this gap visitation complexity is equal to the infinitum over all policies for the worst case state. And then you sort of balance, this is the complexity of learning an epsilon good action in a state balanced by how difficult it is to reach this state. So let's, somebody raise their hand. Lucas?
Yes, thanks. I just wanted to check, is your definition of the problem, do you need to, in the algorithm, be sure that you have an epsilon optimal policy, or can you run an algorithm that doesn't know how good it is and just see how long it takes to get there?
Oh, that's a great question. Yeah, we assume, the algorithm has to know it has an epsilon optimal policy. So it's like a verifiable problem. And used to return an epsilon optimal policy with essentially like a certificate that is epsilon optimal. Yeah, great question. Yeah, so let's say we fix some policy pi and we run this policy for k episodes. Then for any state s, we'd expect to reach the state WH pi of s times k times on average, right? This is the sort of the probability you reach the state under policy pi, and so this is the average number of visitations, right? And so it follows then, if we sort of look at this bandit complexity, if we think about there being a bandit at state s, then to solve this bandit, to find an epsilon good action at state s, we need this WH pi of s times k to be greater than the sum over actions. And so if you just solve this for k, you see that you need k to be greater than or equal to 1 over WH pi of s times the sum over actions. And this is exactly what we have here, right? We have this we have this sort of, this is, now you can see the complexity of sort of solving the worst case S if you're playing the best case policy. And you'll know also we scale the epsilon, so we're actually not concerned with finding epsilon good actions. We're concerned with finding epsilon divided by WHS good actions. And this is really critical because this WHS says if the state is really hard to reach, then you essentially don't care. Like this will be greater than H, say. You don't need to actually even learn anything in this state. But if WH is really large, if you can easily reach this state, then this will be small. It'll scale more like epsilon. And so you need to find a better action. But critically, it's easier to reach, so it's easier to learn a good action. And I'll sort of explain in more detail sort of how this balances out in a later slide. So this is sort of the high-level idea behind this gap visitation complexity. Any questions on it? OK, so again, it sort of just generalizes this idea of a bandit complexity to this case where you have to navigate in an MDP. And then we have the following theorem. There exists an algorithm, Mocha, which returns an epsilon optimal policy with probability at least 1 minus delta after, at most, this many episodes, where it's the gap visitation complexity plus this additional term, which I'll describe in a second, times some extra h factors times log 1 over delta. And then you get this lower order term that's polynomial in S and A and H and is divided by epsilon. And this extra term here, it's scaling as the size of the set opt epsilon divided by epsilon squared. And this set opt epsilon, so if you recall from here, what we really quantified was we said we're learning epsilon over WHS good actions. And so this set opt epsilon contains all the actions that are more than W that are WH over delta optimal, close to optimal. So these are the actions which are that have gap less than epsilon over WH of S. So it's sort of the actions you haven't yet eliminated. You have to pay this 1 over epsilon squared for each of these. And we furthermore have that if the MDP has unique optimal actions in every state, and epsilon is set less than, if we run the algorithm with a setting of epsilon less than epsilon star, where epsilon star is sort of this like minimum over the reachability in the gap, then Mocha will terminate in at most C star of M, which is this best policy gap visitation complexity, and it will return pi star, the optimal policy. So we can sort of run this algorithm. We give it an epsilon. If it can identify the optimal action in this amount of time with this setting of epsilon, if epsilon is less than this, it will identify the optimal policy, and it will return and output the optimal policy after this many episodes. If it can't identify the optimal policy in this many steps, then it will simply terminate in after this many episodes, and it will output an epsilon good policy. OK, so this is the main result, but we can get sort of a few interesting corollaries from this result. First, I want to just talk a little bit more about this gap visitation complexity. So there's a few different ways you can actually upper bound this, and all of them give sort of different interpretations that are related to different sample complexities that appear in the literature. So the first is the one I already showed, which is simply basically this info over pi max over states, and then like sort of this bandit-ish complexity. But then we can upper bound this by something that doesn't contain this info over pi. Now it's the sum over all states and actions. And basically, it's just the minimum over the gap squared and epsilon squared scaled by this WH of S factor, this reachability. And so this sort of quantifies the fact that you always have to pay this reachability to learn an optimal action. And we can further upper bound this by something which is much more analogous to this complexity we get in this online to batch conversion for this logarithmic regret algorithm, which is basically you get a 1 over epsilon times gap complexity. And then we can further upper bound that by S times A times H over epsilon squared, which is this worst case style complexity. And so because we're getting this algorithm that scales with Cm of epsilon, if we upper bound C of M of epsilon by all of these things, we can get corollaries that say like our algorithm performs at worst as this complexity, et cetera. And so in particular, we get that the sample complexity of Mocha is bounded as h to the 5th times S times A over epsilon squared. And so in the worst case, basically, Mocha is nearly minimax optimal. So it doesn't hit the optimal h dependence It's a factor of h squared off of the lower bound, but it gets the optimal SA and epsilon squared dependence in the worst case. And so not only does Mocha get this sort of instance-dependent complexity, it also scales properly in the worst case as you would want it to. Furthermore, we can also upper bound the sample complexity of Mocha in terms of this 1 over epsilon times gap quantity. So this is for general MDPs still. But in the particular case of bandits, we can apply Mocha there. And if you apply Mocha to a bandit instance, you'll see that the complexity of finding an epsilon good arm in a bandit, Mocha will achieve this rate, sum over A times the min over 1 over gap squared epsilon squared. In a contextual bandit, it'll achieve this following rate. WS is like the probability you get context S. And it's simply the inverse probability you receive context S times the sort of number of samples needed to solve context S. And it turns out in both of these cases, these are the instant optimal rates. So sort of the takeaway is basically the gap visitation complexity. It essentially improves upon all these other notions of complexity that appear in the literature. And it captures these very granular instance-dependent properties. And we can, with our algorithm Mocha, we can efficiently learn epsilon optimal policies with complexity that scales roughly as this gap visitation complexity. In the worst case, Mocha is nearly minimax optimal. And on bandits, Mocha hits the instance optimal rate. It's worth mentioning here, I think, that there isn't actually a known lower bound for what is the instance optimal rate for PAC policy identification. You can write down an optimization problem for this, but it's non-convex and it's very, very unclear what the solution is, if we can even hit it. And so we're not claiming that Mocha hits the instance optimal rate for epsilon policy identification. Rather, we're simply claiming it hits sort of this notion of complexity. We've defined this gap visitation complexity, which is a very reasonable and granular notion of complexity. But it might not be the instant optimal rate. In fact, it's almost certainly not. But on cases like bandits and all of that, we can't hit this instant optimal rate because we know what it is, and sort of the structure works out nicely.
Yes, I have a question regarding the rates for contextual bandits that you were showing.
Yeah.
So that has this dependence over WS.
Mm-hmm.
So like, do you really think that this is the instance optimal rate? For example, if WS is smaller than epsilon, then...
Yeah, so I guess I should say for contextual, what I have here is the... this is the complexity needed to find the optimal policy, which means you want to find the best action in every state. And so in that case, this would be, right, like, yeah, one state, one context might be really, really hard to reach. But if your ultimate goal is to find the best action in that context, you still have to pay this 1 over WS. So we also get, with our algorithm, we can write down an epsilon good policy identification for contextual bandits. It turns out there's not in the literature that we know of really even like instance-dependent results for this. So I just stated this here because we can at least state this is instance optimal. But you can also write down an epsilon optimal if you care about that.
All right, okay, thank you.
Yeah, I think someone else raised their hand. Yes, sir?
Yeah, so I have a question. I mean, you mentioned that there are like no lower bounds, but I was under the impression that earlier when you mentioned the work of Marjani and Poutier, they had their like a sample complexity lower bound, which is instance specific.
Right, so they do. I guess the thing, again, to know about well, there's several things to mention about theirs. First, they don't tackle the epsilon optimal, they tackle best policy. And it's much easier to write down an instance optimal lower bound in that case. At the same time, that's still a non-convex optimization problem, and their algorithm actually doesn't hit the lower bound. So if you look at their paper, they simply come up with this complexity that is greater than the lower bound. It's actually worth mentioning our complexity, our notion of complexity, is better than theirs in terms of these like gap-dependent quantities. So,
but there is like one difference because in their setting it's more like a single trajectory-based learning algorithm, and in yours it's like you have episodic setting where each time you sample an episode.
Right. So they're not apples to apples comparison. Like you can't compare them directly, but if you look at sort of the gap dependence and the visitation dependence, we improve slightly on theirs.
Okay.
But yeah, it's not. They're in a slightly different setting, so you can't compare them directly.
And I have another question regarding the polynomial dependence you have. I mean, how much is that? I mean, do you have an idea or?
Yeah, it's something like, I think it's like s to the 4th a cubed or something, and then some like maybe h to the 6th. You can definitely improve it. We didn't focus on getting this polynomial dependence down. I think you could probably get it down to at least an s cubed, maybe even an s squared if you wanted. I probably even just taking stuff out of existing literature that you might have to modify slightly. The actual, I can talk about this a bit later, but the sort of, the reason you get this, basically the polynomial dependence just depends on what sort of a regret minimization algorithm you run in sort of a subroutine in our algorithm, and we just choose to run Euler, sort of, but if you did a slightly, one that maybe had a slightly different dependence, you could improve on this. So it's definitely improvable. It's not horrible, but it's also not great.
Okay, cool. Thanks.
Okay, any other questions on sort of the result, the complexity, any of that?
Oh, there was a question in the chat by Roshan. He was wondering, what do you mean by that one instance specific expression is better than the other?
Yeah, so I guess, are you sort of like referring to this, like?
No, I guess you briefly mentioned.
Oh, right. Oh, versus, yeah, so let me go back to the, comparing to this paper, the Majani et al. Yeah. Exactly. So the main improvement we get over theirs is they pay a min gap. This is sort of the minimum possible gap in the entire MDP, squared times the minimum possible visitation probability. So it's sort of the worst case, and their complexity is sort of the worst case of both. It's like both the worst case gap and the hardest to reach state, but these might not occur at the same state, right? So you could have the minimum gap occur at a much easier to reach state. So what you might hope to get is, rather than, you might hope to get basically the min gap inside the min. And so you basically look at how hard it is to reach that state, but then also how small the gap is in that state. And that's what we get. So we can say, like, the minimum is over states for the minimum gap in a state and the reachability of that state. So it could improve, you know, if the minimum gap and the minimum hardest to reach state don't coincide, ours would be better. But as was pointed out, this is, again, for this, it's a non-episodic setting. So it's not necessarily a direct comparison, but in terms of the general scaling, we do improve on that.
I see.
Yeah. Okay, any other questions? Okay, cool. So I'm going to move on now to the second question we have, which is, well, so we have this notion now of instance-dependent complexity, and we have this algorithm, Mocha, which can hit it. But what does this say about other algorithms that are out there? Are they doing the right thing? And so in particular, we're going to look at low-regret algorithms in general. And so we're going to just define a low-regret algorithm in a pretty generic way. So an algorithm R is a low regret if its regret is upper bounded as C1 times k to the alpha plus C2. And C1 and C2 are just some constants that are like polynomial in SNA or whatever you want. And alpha is any value essentially you want. And so in particular, if you have an algorithm that gets square root of k regret, you can choose alpha to be 1/2. If it's square root of k with some log terms, you just choose alpha to be like 1/2 plus some small delta factor to account for the log terms. Point is, like, this is sort of an algorithm that does well online. And then we're going to look at the following protocol, which we just call low regret to PAC. Basically, the learner runs some low regret algorithm R for k episodes, and they collect some data, which we just denote by script D. And then using this data they've collected in any way they wish, they propose a possibly stochastic policy pi hat. And then they're simply evaluated on the performance of pi hat. And so it's the PAC problem, but we're restricting basically the learner to only play a low regret algorithm. And we have a couple examples where we can show actually that the low regret algorithm, this is suboptimal. And so in particular, this result says on the instance to the right, which I can describe in a bit in a second, the number of samples, the number of episodes, this low regret a learner following this low regret protocol needs to find the optimal policy. This is the key thing here, is 1 over p times delta 2 squared. Well, if we run our algorithm, Mocha, to find the optimal policy, we only need to pay this 1 over delta 2 squared. We don't need to pay for this 1 over p. And now p could be arbitrarily small here. So essentially, this is showing an arbitrary improvement. In the instance here, it's pretty simple. Basically, we just have, it's a horizon of 2. You have like 2 states. So you start in some state S0. And if you take action A1, you transition to state S1 with probability 1 minus p, and state S2 with probability p. And we assume this is the optimal action. So the reward taken, you get in this playing this action is 1. And so any good policy would play this action, essentially. But then we assume there's this other suboptimal action, A2, which will transition to state S2 with probability 1. And so if you're running a low regret algorithm, you're always going to be playing action A1 because it's a good action. And you need to play this to get low regret, which means if p is small, you will not visit state S2 very often. But if your goal is to find the optimal policy and you sort of know this, then you can basically, instead of playing just action A1, you also play action A2. And you'll get to S2 with high probability, and then you'll be able to much more quickly learn a good action in this state.
Question. Are you, like, where is the epsilon here?
So this is best policy, this example. The next example is epsilon.
Oh, okay.
But yeah, this example, right. So you could argue with this example, like, well, yeah, like, but if p is really small, who cares if you learn the good action in this state? Because, like, you know, it's not going to really factor into the suboptimality. So that would be exactly right. So the second example sort of in some ways generalizes this. And now we can say basically if you just fix some epsilon, which could be exponentially small in S. And if you do that and you run this low regret to PAC, to find an epsilon good policy, you need samples that are basically, you need S over epsilon samples. Whereas to find, if you run our algorithm, it will output and it will terminate and output the optimal policy in something that doesn't even scale with epsilon. So it's just some like polynomial in S number of terms samples. And so basically this is saying like there's potentially even this exponential separation between running a low regret algorithm and running Mocha. And the basic idea behind this algorithm is very similar to the last algorithm. You have actions which are informative but very suboptimal, which low regret algorithms won't play. And then you have actions that are the sort of good actions which don't explore enough. And these are the actions the low regret algorithms play. But it turns out to find an epsilon good policy, you need to reach these states more often than the low regret algorithm is doing effectively. And so you basically pay this like S over epsilon term.
Yeah, I wonder how satisfactory it is that the separation happens when epsilon is, oh no, okay, so it goes the other way around. Like epsilon could be as low as 2 to the minus s, but it's not lower. Okay, I see.
Mm-hmm.
It's not in the limit of epsilon goes to 0, because then that you get back the previous case, and that's kind of
right.
It's a bit artificial.
Right. So yeah, this is for any finite epsilon, as long as
right.
Yeah.
Okay. Are you going to explain this example a little bit more? Or?
Sure, I can. Yeah. So I mean, the basic idea is almost the same as what I just said. So now we have big S states, and we have basically big S actions. So there's one action which we'll just denote A star, and A star will transition to any given state S1, S2 up to SS. With probability that decreases exponentially. So it'll transition to the first state basically with probability 1/2, second state with probability 1/4, third state with probability 1/8, and so on, all the way down. In contrast, then, if we play these suboptimal actions, we can get them to transition to any one of these states with probability 1. And so then the basic idea is, well, like, look, to learn the optimal policy will always play A star in S0. And then it's going to reach these sort of other states with some probability. And because these states are sort of decreasing exponentially, the reachability of these states, no matter what epsilon you choose, you're going to have some like rather hard to reach state, which you need to learn an optimal action in to show that you're epsilon good. Because if you learn a suboptimal action in these states and the gap is large enough, then as long as this, so essentially, I guess I could have put the calculation on the slide, but basically, if epsilon is like 2 to the negative n for some n, you need to learn the optimal action in that state. Otherwise, your sample complexity, your suboptimality will be like 2 to the negative n times gap in the nth state. And the difficulty of reaching the nth state is 1 over 2 to the negative n, which is 1 over epsilon. So that's sort of the intuition. Like you have to reach these hard to reach states that are like epsilon hard to reach, essentially, to find a good policy. Is that sort of cleared up a bit? Okay, great.
Absolutely. Yeah, thanks.
And so sort of the takeaways from this is basically that low regret algorithms are not really necessarily doing the right thing if our goal is to find a good policy. They get good online regret, but we can do much better if we just want to find a good policy. As a corollary, this also implies that standard optimistic algorithms are also suboptimal. You can show that an optimistic algorithm that has reasonable bonuses will be low regret, and so therefore these are also suboptimal. They would fall into this class. And it turns out that existing PAC algorithms tend to all be optimistic. And so this basically shows that existing PAC algorithms are also suboptimal. They're unable to capture this complexity. Again, the key insight is that you need to take informative actions instead of like good actions. And this is sort of the main insight for our algorithm. Okay, any additional questions on this sort of low regret thing?
Yeah. So in the low regret definition, you had this alpha exponent.
Yeah.
Isn't that playing a role here?
Yeah, if you look at the actual stated results in the paper, it does. So for instance, like in this example, there is actually an upper bound in epsilon that depends on this alpha.
Yeah, sure. Right.
So it does play a role. I didn't state it in the slides just because of space constraints, but
So
if you look at
that if alpha goes to 1, then you basically have all the algorithms anyway. So
right. I mean, yeah, if alpha goes to 1,
like this, right?
You're back to not low regret. So
yeah. So alpha, like it's the dependence on the alpha that is like really doing something here.
Yeah, for sure. Right. Because like basically the dependence on alpha is restricting the number of times you can play a suboptimal action. Yeah. Okay. So
how does alpha appear actually in the result?
I can't remember honestly off the top of my head.
Pull up the paper really quick. Or
what was that?
Is it complicated or?
No, it's not complicated.
Okay.
Let me just pull up the paper really quick.
Sure.
Okay, so the basic dependence on alpha is it's sort of, I can just read off. Okay, if we go back to here, the dependence on alpha is epsilon has to be less than C1 to the negative 1 over alpha times S to the 1 minus alpha over alpha. So basically C1 has to be less than, so say alpha is 1/2. This basically says that epsilon has to be less than 1 over C1 squared and times S squared. Is that right? Times S. S over C1 squared is what epsilon has to be less than, for example.
Okay. So it kind of
basically you're gonna get intuitively you're gonna assume we run like a standard low regret algorithm that has alpha like less than 1/2 or something, or alpha around 1/2. Basically, this is gonna say that you need epsilon less than like maybe 1 over poly S or something.
Yeah. It limits the upper range for the epsilon.
Yeah.
Okay. All right. Thanks.
Yeah. Okay, any other questions? Okay, so I don't think I actually have that much time left, but maybe I can spend just like a few minutes sort of describing some of the ideas that let us, like the sort of key techniques if people are interested. So, okay, I'll try to keep this brief, but I guess there's two basic ideas I can maybe just talk about the first one. So basically, Mocha is essentially an action elimination algorithm. And there's really two insights that we use to get this sample complexity. The first is we come up with this new error decomposition that allows us to go from this very local notion of complexity, of optimality, to a global optimality, which I'll describe in a second. And then we also come up with this exploration procedure, which is able to like efficiently traverse an MVP to collect relevant samples. So to the first point, basically, the idea is assume that for every state and every horizon, we have some policy pi hat, which plays an action which satisfies the following. Basically, the action played by pi hat, let's look at the sort of optimal action we could play in state S at time step h, given that we then play pi hat. And the action played by pi hat in state S at time step h is within a factor of epsilon hs away from this. And so basically, this is like a local notion of optimality. It says like, okay, given that you're in state S, you play pi hat, come up with an action that is sort of good given that you then play pi hat. And if this holds, then you can say that the global suboptimality of policy pi hat is bounded as basically the sum over the horizons, the soup over sort of reachability, and then this sum over S, the reachable, how easy it is to reach state S times the suboptimality in state S. So this is somewhat analogous. You can think of this almost like the performance difference lemma, for those familiar with that. It sort of is like this gap times the reachability of a state. But the key difference here is that we now have this local idea of how suboptimal a state is. And so we don't actually need to worry about just like sort of how close we are to getting the optimal action, the globally optimal action at every state. All that really matters is that we can like find an action that is sort of like locally good at every state. And it turns out that this allows us to then basically do a fairly simple action elimination procedure to eliminate actions. And so I'll just describe that procedure really briefly. So say we have some MDP we start at some state, or we sort of have this initial state distribution over states, and it sort of goes for h steps and then goes into a termination state. Basically, the procedure we run, which is essentially what Mocha is built upon, is we start by playing some role in policy. Let's just call it pi in. And we play this up to level h. We get to a state at level h, and then we play an action. And we just keep doing this. And eventually, we'll sort of learn what the optimal action is, or a near optimal action is in every state at level h, assuming we reach it with some probability. And so once we do that, okay, we've sort of determined good actions in every state, or reasonably good actions in every state. We eliminate then the bad ones, and we just define pi hat to be simply these like actions we think are good. Then we play a role in policy up to stage h-1. We play an action in stage h-1, and then we play pi hat henceforth. Now, it turns out that the reward you get, the return of the reward, is an unbiased estimate. If we go back to here, it's going to be an unbiased estimate of q of h of pi hat. And so basically, by playing these different actions in the state h-1, we're getting an unbiased estimate of the q value function in the state, which allows us to eliminate then these sort of locally suboptimal actions. So once we do this in stage h-1, then pi hat becomes, now we fix our actions in stage h-1 as well as h, and we move to stage h-2, we do the same thing there. You sort of continue iterating backwards until you've eliminated actions essentially at every stage. And the key thing here is that when you get to a stage, this is sort of where our names come from. When you get to a stage, you just do a Monte Carlo rollout of pi hat. And that gives you an unbiased estimate of the Q function and allows you to eliminate actions. And then using this, basically, if you can sort of quantify sort of how many samples you collect from each state, then you can quantify the epsilon h of s at each state. You can quantify the suboptimality, and you can use that to quantify the global suboptimality. So this is the basic idea behind Mocha. And then sort of there's a lot of details here, which I don't think I have time to go into right now, but maybe we can discuss if people have questions. The key challenge then is how do you choose this role in policy? And it turns out that there's a way you can do this that sort of like is able to efficiently explore the MDP to reach the states you want to reach with high enough probability. But maybe I will close here, and yeah, happy to take any questions.
All right, thank you very much. Nice. Yeah, so I actually think that there's enough time that you can talk about all these details. At least I'm curious to hear.
Okay, sure, yeah. Okay.
Unless people are dying to ask some very important questions, but I think that these are the most important ones.
Okay, cool. Well, yeah, if people are happy, I will happy to stick around. I'll happy to talk some more about it. So this is, yeah, what I just described is sort of the basic building, the basic conceptual idea behind Mocha is let's just do these, eliminate actions in this sort of Monte Carlo way. And so then the question is, how do you do efficient exploration? And so we can do this sort of back of the envelope calculation where, again, let's say we play the policy, let's say we play policy pi, which is sort of the one that reaches S with highest probability. Then we'll expect to reach S on average WH of S times K times. So by like sort of standard bandit rates to find an epsilon H optimal action in this state, it might take something like A over epsilon HS squared samples, which means that to do this, if we were playing this policy pi I just described, we need K to be greater than A divided by WH of S times epsilon HS squared. And so now this is the key thing. If we set epsilon H of S to be equal to some beta times epsilon, the complexity we actually care about in the end, divided by the maximum reachability of this state, then we only need K to be greater than A times WH of S divided by beta squared epsilon squared. And the key thing here is that this setting of epsilon, because of the way the reachability factors into the suboptimality, you get this cancellation of WH of S. And so our final policy will be SH beta epsilon suboptimal. And we have to only collect number of episodes that doesn't scale inversely in the reachability, which means you sort of get this cancellation in the reachability. You sort of, if a state is hard to reach, it doesn't factor very much into the suboptimality, and you can scale how many samples you collect from that by this reachability. Now, this doesn't actually work in practice, this sort of strategy here, because you can get you'll end up with a suboptimal dependence in S. And so it's not going to be minimax or nearly minimax optimal in the worst case. And so to overcome this, we propose this procedure we call learn to explore. And this is not really, we sort of have some novel tweaks to it, but the basic idea has appeared before. It's similar to the RMAX algorithm, for those familiar with that, as well as some of these reward-free learning papers. They use similar ideas to traverse an MDP. And so the basic idea is we just want to come up with basically a map to explore our MDP. We want to break it up into explorable sets. So let's just start running our learn to explore algorithm. We'll just set this set X, script S to be all states and actions. And we sort of iterate then exponentially. We'll just assign a reward of 1 to every state action in X, run a regret minimization algorithm on the MDP. And we run this for basically 2 to the J times polynomial SAH episodes. So J is increasing exponentially, so we basically exponentially increase the number of samples we're taking. And then after running this regret minimization algorithm for this long, we're going to be set xj to be all the states and actions that were visited more than some number n min times over this 2 to the kj number of samples, episodes. And then we remove these SNA that are in xj from X, and we store the policies we just ran, and we just iterate. And so basically the idea is like, look, you're setting the reward to 1 for all the states and actions you haven't yet reached very frequently. Then when you run a regret minimization algorithm on this MDP, it's incentivized to explore all these states and actions it has not yet reached. And so if you sort of run this long enough, you can reach all of the states and actions that are easily reachable. And furthermore, you get this set of policies which are like essentially like a map that allow you to then like guarantee you're going to re-reach these states. And so the theorem we can get from running this procedure is the following. Basically, with high probability, the sets returned by learn to explore xj satisfy this. Basically, the reachability of this set, right? So the sum over all SA and xj for the sort of policy that reaches this best is 2 to the negative j. So by running essentially for 2 to the j samples, then we can guarantee that we're going to decrease, these sets are going to contain harder and harder to reach that states, which makes sense, right? If you run more, you would expect to reach these states more. And so if we're not reaching them early on, that means they're hard to reach. Furthermore, and this is a really key point, by executing all the policies again, all the policies we ran in this procedure that were in this exploration stage, we can guarantee that we'll visit every state action in xj at least like half the number of times we visited in the first draw. And so what this gives us is it gives us a set of policies that is essentially like a map over states and actions. We know that if we run these policies again, we can guarantee we're going to reach these states and actions a given number of times. And then this allows us to actually like learn, to guarantee that we can like learn good enough actions in them. And then finally, the total complexity of running learn to explore is polynomial in S and A and H divided by epsilon episodes. And so sort of learning this exploration map over our MDP is like a lower order term. And this is where this like that lower order term you saw in the complexity in our main theorem comes from. Okay, and so great. Now we can actually use this result as combined with our error decomposition to show something about what we learn, what we're able to learn. So again, assume we ran learn to explore. This right here, the first two lines, or the first inequality on this is from our proposition that decomposes the error. And so we're just going to upper bound this by basically the partition. So let's just sum over j. Xj is the partition generated by this learn to explore algorithm. And we'll just pull the soup inside that. Furthermore, let's assume that epsilon hs, we set it to be the same thing for all s that are in a given partition. In particular, we'll set it equal to 2 to the j times epsilon divided by h. Now, if we do that, then this term here becomes, well, epsilon h the same. Epsilon h of s is the same, so we can pull it out. When we pull it out, we just get this 2 to the j times epsilon over h. And now the key thing here is we have this reachability of set xj to the h. xjh. Now, if you recall from our previous theorem, the reachability of this is decreasing exponentially in j. And so this is 2 to the negative j, which cancels with this 2 to the j. The h cancels with the h, and you end up with an epsilon times the logarithmic factor.
So quick question, what's the definition of xj and h?
Yeah, so I should have made this clear. So xj, what I was using here is simply this partition returned by this learn to explore algorithm. And so it's sort of a set of states and actions that can be like reached at roughly the same rate. The key property is it satisfies this. So we can upper bound the reachability. So xjh, the subscript h denotes that in reality, because our algorithm is doing this thing where it segments based on the horizon, we also do this learn to explore procedure where we segment based on the horizon. And so xjh is sort of like jth reachable states and actions at stage h. Does that clear it up?
Okay, yeah, it's like stage-wise, you are basically running the same procedure.
Exactly.
Okay, that's what I thought, but I wasn't sure.
Yeah. Okay, so basically, the point is if we set epsilon h of s to be this value, 2 to the j times epsilon over h, we can get an epsilon optimal policy. And then the crucial thing is that based on sort of our guarantee that based on this guarantee, that if we rerun policies in pi j, we can visit all these states at least n min j over 2 times. In our setting of kj and n min j, you can show that the number of samples needed to collect basically 1 over epsilon hs squared number of samples from every state in action. If you just plug in all these values, if you work out what kj, n min j, and all these end up being, you can upper bound this by s times a times h to the 4th over epsilon squared. And so basically what this says is that like, because you can weight by the reachability, if you weight properly by the reachability, you can both guarantee an epsilon optimal policy and using this sort of map over states and actions, you can guarantee that you can collect enough samples to actually find the epsilon reachable, to find epsilon optimal actions. Okay, and so then basically, that is basically the idea behind Mocha. The only sort of, there's a variety of various tweaks and like technical things we have to do to get this to actually then work for this full algorithm. But these are the two main building blocks. And the key idea is like, we run this, we sort of gradually decrease the tolerance we're sampling at, right? So we ultimately want to sample at this tolerance epsilon, but we start just by sampling at this tolerance like h, and we gradually decrease it, and then eliminate actions that are epsilon L suboptimal at every stage. So we never sample an action more than like 1 over its gap squared times. And if you do that and you couple it sort of with this like learn to explore procedure, so now we do learn to explore only over our active states and actions. If you couple it with that, you can show that you only actually sample any given action like 1 over gap squared times. And if you sort of like work out sort of what you get combining these techniques, you get the gap visitation complexity at the end. So that's the, do people want me to keep, I can keep going, but I'm also happy. That's sort of the high, that's I guess a little bit more detail on what Mocha's doing. Those are the main ideas behind Mocha. I can go into a little bit more detail if people want, but maybe I'll sort of see if there's more questions.
It's pretty clear, I think. You basically learn this best way of visiting individual states. And after knowing those, you can then do this partitioning and yeah, figure out with this elimination algorithms and rollouts the rest.
Yeah.
So does this method actually guarantee that you're going to be visiting states proportionally, at least, to this capital WS, or that's not important?
Yeah, so that's a good question. So this gets into some of the more like technical details, I guess. So what we end up doing is because as sort of intuitively, you don't, again, this maximum reachability sort of quantifies like this worst case of like how much a state could like mess things up. And so basically what we end up doing, if you look at the paper, the full algorithm of the paper, we run this initial stage where we just try to eliminate actions that are epsilon over WH of S suboptimal. And that's what this is essentially doing. Then once you run that stage, it turns out you have to run, we end up running another stage, which sample at a slightly higher rate, which guarantees that your actions are like epsilon, or your final policy is epsilon optimal. I don't know if it's kind of subtle. Basically the idea is like you want to you first just eliminate the epsilon over WHS actions, suboptimal actions. You get those out of the way, and then you run the argument I just presented. And the reason we break it up into 2 stages is sort of for like technical reasons. Yeah, I don't know if that cleared it up or just made it more complicated.
Yeah. Well, that made total sense. Well, maybe I'm still not understanding everything, but here on one of the pages say that this takes a total complexity of SA over epsilon squared episodes. So maybe I'm not getting this right, but so like how is this good? And this is just instance independent.
Oh, like right here?
Right, yeah.
Yeah, so right here, so maybe I can show this is sort of more of a back of the envelope calculation to show that like how the procedure works, or like why the procedure works, how it gets minimax. To get the instance dependent, it really crucially relies on the fact that, I have a slide on this, maybe I can just put this slide. It really crucially relies on the fact that you will only sample an action while the maximum reachability times the gap is greater than epsilon, right? Epsilon L, where epsilon L is sort of this thing that we decrease exponentially. And so we just decrease it by a factor of 2 at every time, which means you don't end up sampling a action more than basically WH of S 1 over WH of S times delta of S squared times. And so when you sort of work that out, when you sort of do this, like break it up now into this like exponentially decreasing epsilon, you can show that you eliminate actions early on if they're suboptimal by a lot. And then basically you don't pay for them in this final S times A over epsilon squared terms.
Right. Okay. That makes sense. That's great. Okay. So does anybody else have questions? Ronald. Yeah. Hey. What's up? Go for it.
So hello. So thanks for your interesting talk. So I'm interested in whether you have an intuition whether this low regret result also extends to the undiscounted setting.
So I guess we're sort of working in the undiscounted setting. So maybe could you make
non-episodic? Sorry, non-episodic.
Right. Yeah, that's a really good question. So I think the issue is that so it's important for the episodic setting. We rely on the fact that you can essentially like restart after H episodes, and so like you can keep like trying the same thing over and over again. Whereas in the non-episodic, you kind of are like stuck in the single trajectory, and then you run into issues of like, well, what if you get stuck in a bad state, and that's hard to get out of and stuff like that. So I'm not sure our techniques would extend directly. I suspect you could probably show something similar. I think conceptually though, the idea is probably still true in that if you run a low regret algorithm in this non-episodic setting, it's still going to be doing this thing where it's like taking actions that it thinks are good, even when maybe the informative actions that would help it learn more, it won't end up taking these. And so I think that would probably still hold in non-episodic. Now you'd have to go through all the work of extending our paper to that setting, but I suspect the sort of final conclusion could probably be shown to hold.
Yeah, I mean, so the thing that I was thinking was that when you have this episodic setting with this episode length H there, then you can say somehow that with respect to this episode, it doesn't pay to insist in some transition or something. Whereas in the undiscounted setting, this doesn't hold anymore. There you don't have this H. You only have a diameter for a general distance between states. And so I'm not sure whether this is something that's really particular to the episodic setting, maybe. I'm not sure.
Yeah, I guess I need to think about that more. I mean, I think, like I said, my intuition is that like probably you could show low regret or still suboptimal if you want to get if your goal is to find a good policy. But I'm not as familiar with all the sort of the technical intricacies of the non-episodic setting. And so I probably need to dig into that a little bit more deeply to really like fully answer your question. Certainly, though, I mean, like algorithmically, there's definitely technical things in our algorithm that wouldn't directly extend, like I said, to sort of the non-episodic setting. So there'd definitely be technical challenges that we'd have to overcome to extend that. And I'm not certain, what would be involved in doing that.
Yeah, thanks.
So I was wondering about this technical result that you showed that you related to the performance difference lemma. So that also came to my mind, like very vaguely, that it sort of looks like that. But I'm just wondering about like the details and how can you put that supremo or policies there on the right side.
Right. So yeah, the proof is actually fairly simple overall. I didn't put it in, I didn't create a slide for it, but if you want to look at the paper, I think it's pretty intuitive. So the basic idea, I mean, like intuitively, the idea behind it is like, let's say we learn an epsilon S optimal action in every state at level H. And then we go back to stage H-1 and we learn a locally epsilon optimal subaction, locally epsilon suboptimal action. then sort of the suboptimalities add, because if we're locally suboptimal, we know in the next stage, like we're this factor of epsilon away from the optimal policy. And so if in the previous stage, we're also a factor of epsilon away from the optimal policy, the locally optimal policy, then we're going to be a factor of 2 epsilon away from the total, the sort of globally optimal policy. So that's the intuition. Now, making this work with why you get the soup over pi here is that when you look, so the basic issue is that the action, you can think about the action you're going to be playing at stage H, this pi hat of H, you don't really know sort of, it could be any action. It's hard to quantify what sort of the locally optimal action will actually be, like what this A is going to be here. And so you can actually refine this a bit. You don't need a soup over pi. You can do like a soup over, like, you can get something like a soup over epsilon optimal policies, I think. But the basic idea is that because the action you're taking at stage H is like, could really be anything, then the sort of like how likely you are to reach a stage in the next episode, a state in the next episode, it's kind of hard to quantify without just upper bounding it by all policies. I don't know if that makes sense. So basically the idea is if you're playing pi hat at stage H, it's hard to quantify what the actual visitation distribution of pi hat is at the next stage, because it's just some policy. It's hard to relate pi hat to pi star. It's just some policy is going to induce some visitation distribution at the next stage. And so we just upper bound that by the soup premium over all distributions.
Right. Because so the performance difference lemmas, that would give the visitation probabilities of the optimal policy there, but also there the gap between Q's between the optimal action and pi hat. So basically you just replace that optimal action with this max over the...
Right, yeah, so to relate to the performance difference lemma,
I'm pretty sure that's what the performance difference lemma says. That you would get like W of pi star there.
I think it's W of pi, if I recall. It's like W of pi times the gap. Is it W of pi star, performance difference lemma?
Right, so you're comparing two policies, pi star and pi hat. Q belongs to pi hat, right? And W belongs to pi star.
Right.
Well, you can do it both ways, actually.
Right.
Depending on how you choose the roles. And here you're replacing pi star with this other, well, this kind of like policy that picks the maximum of Q pi hat.
Right. So maybe I can just, I don't know, maybe I can just share the paper. I don't know if that would, if I could just show you the calculation in the paper, I think it'd make total sense why this works.
Yeah, I think that makes sense.
But yeah, yeah, so basically the soup of pi comes from the fact that
aren't you guys saying that this would also follow from the performance difference lemma?
This wouldn't follow. I don't think this I don't think it directly follows from performance difference lemma. It's just in spirit similar.
Okay.
Yeah.
Right. Yeah. I was just suggesting as well. That is what the performance difference lemma would give, but here there are some serious differences because you replace one of the policies with something else there, and in some sense you're getting something worse, but you're also buying something.
What is being bought?
You can get this local notion of suboptimality. So basically, the performance difference lemma, it has, instead of an epsilon, a local suboptimality, it has a gap, right?
Okay. Anyways, we can take it offline, or like just think, individually about this. Yeah.
Yeah, I think I would just recommend looking at the paper. I think the proof is pretty clear in the paper. It's lemma. It's on page 27. It's like a one-page proof, so I think it's.
All right. Okay.
I think it's pretty clear from that. It's hard for me to like describe without just like writing out the math and why this works.
Yeah.
All right. Okay. I'm gonna check that out. Yeah, so this discussion starts getting very technical, so maybe it's best to really go off the record.
Sure.
Like already getting very deep into the details. So if you were saving some controversial questions for the end, maybe this is the right time to ask them.